I've got very similar examples. We have a panda and add some noise with some magnitudes, and we have gibbon with confidence more than source image in panda. You know, it's really big trouble. It's called adversarial examples and adversarial attack. And this year, it's such a big trouble that this year Google Brain started the competition on Kaggle. The main idea is to develop as much possible types of such adversarial attack. I showed you the simplest one. We take image, then take some data and just add and want to predict another class. But it's not very. It looks very like a very sharp image. And the second type is to find the way how to defend yourself. It's not very nice that everybody could take your model and write another model to fool it. So I suppose guys from Google don't like this. It was just fun, but we want to generate photorealistic images. And in our previous problem statement, there was an issue that we haven't got a way how to compare whether image look like natural or not. And so so this is where generative adversarial networks is coming. It is a quite interesting idea which came from game theory, and main idea that you have two agents and you want to make them compete. So in our problem statement we'll have two networks. One is discriminating network, the second agent is a generative network, and we want them to compete. We'll train discriminator network in such way. We'll take real images and some fake images which were generated by generator, and try to predict ones for real images and zeros for fake images. So generates just a binary classificator. Not a classificator to many classes, it's just a binary classificator. At the same time, we want our generator network to take some noise vector as input and produce such tensors to fool this discriminator network. We want discriminator network to predict ones for fake images. So we have two losses here. It is loss for loss, I suppose, for discriminator. Yeah, we want our data to be specified correctly, and we want this loss is for generator. We want to fool our discriminator when we sample noise from some distribution. So that's all, and oh, this one more. As we have loss, this loss is differentiable, and we can solve this task with a gradient descent. It's okay, but there is no guarantee that you will find a good solution, but you can always try to do it. So the good solution here is called the equilibrium point. It is a point when if you improve generator, you will generate your discriminator, and vice versa. So let's try. Let's try this one. It's some code for discriminator in PyTorch. You know, it's if you want to try something in something what is very close to state of art, it's a very good library to code. You see these some blocks, so we have both of these classes can define our discriminator model. Then we'll define the generator, some architecture, some parameters, it doesn't matter. Then we'll take some data set. It is a data set of faces. I don't remember how it's code, but maybe I can share it if anybody is interested. And then we solve this minimization problem, optimization problem. Oh, sorry. And this is evolution of generator. You know, we are starting from totally random, and then we train our generator to full discriminator, and you know, iteratively it improves. In the last phases, they looks not very good, but they are very close to real one. You know, we have some problems with eyes, but maybe we could fix it with a deeper architecture or something like that. But it's quite nice that starting from total random we can generate really photorealistic images. But there are a lot of difficulties here. The first one is the generation of large-sized image. Large-sized is more than 128 by 128 pixels. It's really hard. The problem of variability of real-world images. So if you want to generate only faces, it's not a problem. If you want to generate the whole classes from ImageNet, then you are in trouble. As I know, it is not possible by the current moment. Also, there is no guarantee that this minimax game will converge to equilibrium state, as I said. It is also difficult to keep d of x and g of z on the same quality level, because initially d of x has a much simpler problem than g of z. It's not initially it's not a problem to discriminate random noise from real images. That's why usually you should do something with that. And quality assessment is also an issue, because it is an issue for all generative model. How to assess whether this image was generated, or whether this generated image was good or not. Usually some kind of mechanical torque people use, and so on. Something from the state of the art. I suppose that it is CIFAR10. It's a data set of 32 by 32 pixel images of 10 classes. I don't remember actually what classes, but I suppose that maybe cars and animals and something. So, where is generated? On the left side we have real images, real feature images, Christ. And on the right we have the generated images. You know, when we have small resolution images and you not very close to the monitor, then it's very hard to discriminate which of them are generated. The next one is simple. All these bedrooms are generated. Quite nice, yeah? What I've been talking about variability and size. You can generate very photorealistic bedrooms, but if you want to generate the real world data, like for example ImageNet dataset, then you'll have trouble. This is what you usually will see. This is what you will usually see if you do a lot of tricks to improve the stability. You know, it's not a very photorealistic docs, as I suppose. We've tried this technique to build images. We have a lot of images from Instagram, and we want to build the network which generate Instagram posts and try to become influencers in some sphere, but we've also faced this problem that we generated some textures, very strange textures. Some concepts of designing this experiment, what you should do to improve the stability of this task. Well, as I said, that discriminator should have less parameters than generator, because discriminator have a simply here problem. Use good activations, some tricks to improve the stability, normalize the images to floats from -1 to 1, and so on. You can see this link, a lot of hacks here, and a good article by a young fellow, Improved Techniques of Training GANs. So this is improved one, very improved. Speaking about generator, as we have activations, as we have normalized all our images in its range from -1 to 1, you should use the 10th on the last activation layer. Use some stability tricks, use dropouts, use good activations, so do everything you can to improve this. It is very funny, but how to use this technique to improve something in the real world, how to make the world better. And one of the tasks when we can use GANs, not for fun, is the image segmentation. Now it's a very common computer vision task, and the idea is for each pixel of image to classify each image of pixel. For example, then we have segmentation, the road, the cars, the buildings, and so on. Another example, you can use image segmentation to remove the background. For images, it's quite popular nowadays. But the problem that optimization issue there, that optimization problem uses per pixel loss functions, and per pixel loss functions they do not reflect many aspects of segmentation quality. What I'm speaking about? You have forests, and then in forest you have some blob. I really don't know what is it. You have problems with segmentation on the road, and here some problems. It is so because the model don't know that in real image, in real life, it is very unlikely that somewhere in the sky you will have a circle of roads. It is the issue of per pixel loss. So how to fix this issue? Okay, let's minimize not only the per pixel loss, but also minimize some called GAN loss. We have our segmenter model. Segmenter model takes image, forwards it through the CovNet and gives some class predictions, and also we have the ground truth masks. And then another loss takes predicted mask and real mask and gives a penalty to our segmenter if generated masks don't look like natural photorealistic masks. It tends to work like this. We have inputs, we have ground truth. With no adversarial loss, we have some troubles in the sky. But using adversarial loss, it's much more stable, much stable. Interesting fact that when we use an adversarial training, on the training set we have we have less accuracy, I suppose, but on the validation side we have more accurate prediction. So there are many other interesting things about GANs. We have conditional GANs. It is when you have condition. For example, generate me random man, generate me random car. So when you build the sampling process from conditional distribution. Stacked GANs is quite nice technique to improve the result of generation for higher resolution images. Some different models, different generative models. We can apply this to other domain, to generation of audio, video, and so on. Other interesting practical tasks, for example, image super resolution. You can have a small image, and then you can resize this, make it bigger, and it will be very sharp because we just copy pixels. But you can build GAN to make this image more realistic, and it's work quite nice in practice. Maybe I have some links to articles. So for today it's all. Short summary. Convolutional neural networks worked perfectly in CV tasks, but don't forget that we have a serious problem called adversarial examples. What about speaking about Gen framework? It's a very interesting idea, and it's not only for fun, but also can be useful. And you see that there are a lot of tricks to improve these things. So I suppose further improvements in this area are expected. Thanks a lot. Today is so.
Okay, thank you. Any questions?